if you follow chess, but you know, when grandmasters were losing to AI, they started to realize that there's a style that AI has that is different, and it was entirely missed basically by human learning. And Gary Kasparov had a paper on this in, I think, Nature, talking about how fascinating it is to one of the best chess players of the last century to see another grandmaster play and learn from it, like the intuition that you can enhance from playing against AI. I kind of feel like the same sometimes. Sometimes I'm completely lost and I don't have any intuition sometimes, but sometimes I'm like, oh, I see.
That's really interesting.
Yeah, and I love it. And I think the domain where I can say more of that is the diffractive computing. It's really, I won't talk about it today, but I'll talk about it in Boston. It's amazing how sometimes you see what it does and why it does only after you see the solution.
Yes, you have to see the answer first, and then
Okay, so I will open the session for participants to come in, if it's okay.
Yep, I think it's good. It's a good time.
Okay, we started it, so I think
So when was UNIST established?
Actually, 2009. So not a very old school, just a little bit over a decade. Yeah.
Great. It's having also undergraduate, graduate, or is it following more of a graduate focus?
No, it's both undergraduate and graduate. So I think you'll be familiar with KAIST in Korea. So it's like the same system.
Wonderful.
Yeah. So
is
focused,
is it purely government initiative, or is it also having some private investment?
It's purely government. Yeah. So it's a little bit different. UNIST was a little bit had some funding from different organizations first, but then now it's totally government. Yeah.
I see. Yeah. Wonderful. And how has COVID impacted your university? So was it delaying, like closing campus for a long time, or how did you handle it?
Well, so we didn't entirely close the campus for, like, compared to the US, it wasn't that long. It was, the entire closing was maybe a few weeks.
I see.
And even then, it wasn't just entire closing. It was like minimal crew. But right now, so most of the people in Korea didn't get COVID. So right now it's a problem because now it's surging.
I see. So I see. So what is the vaccination rate in Korea?
Vaccination rate. So from what I remember, it's over 80% for up to the second dose. So even the third dose, it's like 50%, I think. Yeah.
And Omicron is the one that is the dominant.
Yeah, so that's the problem right now because
I see.
the vaccines don't really work.
Yeah. Well, I guess we'll have herd immunity.
Yeah. Yeah. So that, I guess that's basically what we have to wait for.
Yeah.
Yeah. So I heard that all restrictions on the masks are gone in the US right now.
Depends on which state you are. In my, school, UCLA, we have to wear masks indoors, and soon we will be able to take it off. I think April 1st, if I remember.
Okay.
But Texas is, for a long time, it's different.
Yeah.
As an example.
Okay, so I think we can start. Professor Park, will you begin the session if it's okay?
Okay.
Okay.
Okay, so welcome everyone. Thank you for joining today's session on the UNIST Distinguished Lecture Webinar Series. So actually, this is the first speaker today that we have for this series on smart healthcare. So I actually cannot think of a better person to start this series than Professor AYDOGAN OZCAN. So he's gonna give a talk today on AI-enabled computational imaging for biomedical applications. And let me just give a brief introduction to today's speaker. So he actually holds many prestigious positions. So he's the Chancellor's Professor at UCLA, and he's also HHMI Professor at Howard Hughes Medical Institute. And he holds various positions, so such as also the Volagnew Chair for Engineering Innovation at UCLA. And I just wanted to introduce a few of the awards and honors that he has received, but like I printed it out and it's like a few pages. So if I read them, it's gonna take the full hour, so I'll just skip that. But I think I can say that he's also a highly cited researcher by the Web of Science. So he's one of the most cited researchers nowadays. And I can briefly say that the Howard Hughes Medical Institute, it's a very famous philanthropy source that only supports people, not projects. So they chose this person as a person who can make impact on society. So he's making impact in both basic research and also in translational research. So without further ado, let's please welcome Professor OZCAN.
Thank you very much for this generous introduction. Let me share my screen. Hope you should be able to let me quickly try it again. I guess there was a small problem. All right. Hope this is working.
Okay, we see the slides. Thank you.
Wonderful, wonderful. So again, thanks for this generous introduction and for having me here today. It's my great pleasure to talk to you about some of our work on computational microscopy, computational imaging, and applications in biomedical space, especially powered by machine learning and deep learning. So first, I'd like to briefly tell you more about my lab's general mission motto. We aim to democratize advanced measurement tools by creating computational interfaces that can measure sense with the same resolution, precision, sensitivity, specificity as you expect from lab-grade counterparts of these devices. And what I'm sharing here with you are some examples from our previous work where using inexpensive interfaces, computational interfaces, we've converted mobile phones into microscopes, all the way from perhaps work that is more than 10 years old, to bright field microscopy, to fluorescence microscopy. It's come a long way. You can actually nowadays turn a smartphone into an inexpensive handheld microscope and be able to see viruses, nanoparticles, and even single DNA molecules. For example, this one is a dark field fluorescence microscope, where with simple silane chemistry, you can actually stretch, for example, DNA molecules and label them with intercalating dyes. And over a relatively large field of view, you can detect and size individual DNA molecules that are fluorescently tagged. You can also utilize these images to size DNA molecules with about a kilobase pair sizing accuracy, which would be very useful, important for example, looking into copy number variations. So you can utilize smartphones as advanced detectors, imagers, despite their compactness, cost effectiveness, thanks to economies of scale, and wide availability. This one is another smartphone-based microscope, but this time it's a multimodal mobile microscope where you can do bright field microscopy of samples and fluorescence at 2 different colors. So this has 2 fluorescence channels. In collaboration with a Swedish group, we've utilized this mobile microscope as a reader for next generation sequencing and performed using colon cancer tissue samples, in situ mutation analysis, targeted DNA sequencing, where basically at the subcellular level, we were looking into rolling circle amplification to differentiate mutant and wild type with 2 different fluorescent colors channels. And you can actually superimpose and look for basically these fluorescent signatures of rolling circle amplification to do basically a single nucleotide mutation analysis with colon cancer patients, demonstrating how far you've actually we've come to utilize these devices for performing advanced measurements that you really normally perform with lab grade $20,000, $50,000 microscopes as a replacement. In addition to converting the smartphone as a basis for advanced measurements, sometimes we also took out some components from smartphones, especially CMOS imagers, those 5 megapixel, 10 megapixel imagers. You can take them out and you can create computational microscopes that I'm highlighting here on the left. For example, this one is a lens-free computational microscope where the main component of this is the same CMOS imager that our mobile phones have been using. If you look inside, it's as tall as an iPhone and very lightweight, on the order of less than 200 grams. And different than traditional light microscopy tools, this is a transmission microscope where you place the specimen, for example, a tissue slide, histopathologist slide, blood smear, or pap smear. In this sample tray, which goes right in front of a CMOS imager. This is exactly the same CMOS imager, 5, 10 megapixel that you have in your cell phones. And the rest is just a simple illumination unit. It's a computational microscope where, as we shine light, we capture holograms, diffraction patterns of these tissue samples or different kinds of samples, which are reconstructed. And the function of these different LEDs is to virtually divide each pixel of a CMOS into smaller subpixels. We call this pixel super resolution, meaning that by turning on and off these LEDs, you can actually virtually create subpixel level resolution. And take, for example, a 10 megapixel imager and convert that into 1,000, a billion useful pixels, achieving diffraction limit resolution across a very large field of view. These are compact, these are telemedicine friendly, which means it's especially useful for digitizing microscopic images of tissue samples where you can actually transmit these images and get them reconstructed, for example, in a different part of the country where you have access to pathologists, etc. This is an earlier generation of one of these computational lensless microscopes where we're looking at thin blood smears infected with malaria. For example, these are standard bright field microscopic images. These are benchtop microscopes looking at thin blood smears. And for example, this one is a Plasmodium falciparum, a malaria infected red blood cell in this case. These are Giemsa stained, nicely revealing with a standard microscope the infection, which could be useful for tracking peristemia and diagnostics for malaria. The same fields of view are shown here with our computational microscopes. This is the phase channel of these holographic microscopes, nicely revealing the same contrast for those parasites invading red blood cells. In addition to being compact, cost-effective, the biggest advantage of lensless microscopy is its field of view. You can look at a large area because the sample directly sits on top of a CMOS imager. That's why these kinds of microscopes are also called on-chip microscopes, chip-scale microscopes, and you can actually zoom in over a large area and start conducting high-end microscopy over a large field of view with a distant resolution. The field of view advantage is also shown here with histopathology slides. This is a tissue section, breast tissue section. The raw images acquired by this lensless microscope are shown here. These are speckle-like patterns, transmission images. This is a connected tissue, so there is literally no opening here. Everything is a thin section of standard histopathology slide. A traditional light microscope for whole slide imaging purposes will need to scan this area perhaps a couple of hundred times to synthesize this kind of an image. So this is approximately a 30 millimeter square active area of CMOS, which gives us that imaging field of view. These are unit magnification microscopes. These holograms are reconstructed to give you these subcellular features. And it nicely matches a traditional light microscope, except there are no lenses, and everything here is a holographic reconstruction engine, which takes these holograms and reconstructs the sample plane. There are different ways of reconstructing these. I'll give you maybe another pointer, because deep learning is now the standard, gold standard, I can call it, for reconstructing a lot of these holograms. And this is a colorful image synthesized by a lens-free microscope. It's a lung H&E stained histopathology slide. Again, the field of view advantage is highlighted here compared to the field of view that you have with lens-based microscopes. You can zoom in and reveal the images of various different scales by continuing to zoom in this image. This is captured with a bare pattern of the CMOS imager, so which means to synthesize these colorful images, you shine light at 3 different wavelengths at the same time, and using the diversity of the bare patterns within a single hologram to demosaic and actually utilize all the color channels to synthesize these kinds of images using holographic microscopy. In addition to microscopy, we're also very much interested in utilization of mobile instruments for sensing. And these are some examples of our former work where we utilize the smartphone as a sensor. Pathogen detector, for example, this is a sandwich immunoassay with capillaries that we devised to use a very old, not so smart anymore, old version of a mobile phone as a sensor. This was a few colony forming unit per mil level of detection sensitivity for E. coli particles in milk and water samples. This was one of the first applications of basically the mobile phone as a direct sensor of pathogens. This is another example for Giardia cysts. These are waterborne cysts that are resistant to chlorine, and they can survive in cold water. That's why we created these field portable disposable cassettes that filter out the correct size of the cyst, and with some fluorescent tagging. This is a fluorescence microscope that is specifically geared to detect Giardia cysts and recognize them without the need for a microbiologist. Some other examples are shown here. This is a Mercury Ion Detector. It's based on gold nanoparticles that are coated with an optimer that specifically binds to mercury-2 ions. As a result, there is clustering of these nanoparticles in the solution where the clustering amount is directly correlated with the concentration of mercury ions in drinking water. So by looking at the transmitted light at 2 different colors, we can understand the shift due to particle size clustering. And this is a very inexpensive sensor that is also rapid to sense 3 to 4 nanograms per mil level of mercury contamination rapidly and in a very inexpensive attachment to the smartphone. So some of this work has been commercialized as well. So I started up a company that commercialized test readers for lateral flow tests. chemiluminescent, colorimetric, fluorometric tests, like a universal reader for various different lateral flow tests. And those products are still in use through our IP and through companies that licensed our work and that also acquired the company that I started. So these are really products, IP that led into new products in the market that are really being used in professional settings for reading different kinds of sensors and tests. So today, I'd like to tell you how our work on imaging, computational imaging and sensing has been empowered by machine learning, by deep learning tools. How modern machine learning, data-driven statistical learning tools have been helping us to upgrade, so to speak, our understanding of computational imaging and our reconstruction, image enhancement methods. So a lot of what I've shown in the past few slides were coming from physics-based reconstruction methods, and they were actually reconstructing, for example, holograms based on the understanding of light-matter interaction, wave propagation, solutions of the Maxwell's equations. But with the advancement created by deep learning in specific, you can actually establish some various interesting methods to reconstruct, to enhance, and to transform images. And that's going to be the topic of my talk in the next several slides. So you can take a deep neural net as a function approximator, which means whatever I've shown you before, let's take, for example, hologram reconstruction. We have some ground truth methods that can reconstruct a hologram and reveal the complex information of the cell or the tissue sample based on Maxwell's equations, wave equation, and solutions to the wave equation. Well, now the question is, perhaps you can actually do this faster and perhaps better if you were to train using image data, holograms input, and ground truth coming from other methods of reconstruction, and train a neural net to do this inference, image reconstruction, much faster. A lot of the past decades, when you talk about inverse solutions to imaging problems, the solutions were relatively slow and iterative. Now, with deep learning through image data, access to the ground truth coming from other methods, you can actually understand how you can speed up this image reconstruction process to be much faster and without any iterations, without any guess and correct type of loops that are commonly involved in solving inverse problems. In fact, that's one of the first applications that we took to reconstruct holograms using deep neural nets that were trained with ground truth so that you can actually mimic what traditional physics-based reconstructions were doing, except in a single feed forward rapidly to reconstruct these holograms. That's not just an exotic transformation. That's actually empowering mobile instrumentation that are based on digital holography to get smarter and faster. For example, this one is an imaging flow cytometer that's working based on on-chip holography. Different than the previous result that I've shown you, this is in flow. As samples without any labels, it's a label-free imaging flow cytometer. As samples are flowing based on these on-chip holograms, we're reconstructing them using deep neural nets, using even a simple laptop without any iterations. Beautiful reconstructions can be achieved over large depths of field, which means using the power of deep learning as a reconstruction engine for holograms, you can actually create these beautiful images on the fly. The throughput of this kind of a cytometer, label-free cytometer, is on the order of 0.1 to 0.5 liters per hour. So you can screen very large volumes without labeling and reconstruct at the microscale the contents of these water samples. This is plankton that we have captured from Los Angeles coastal line and reconstructed them using basically a laptop powered by deep neural nets performing this image transformation, image reconstruction from a hologram to a beautiful, colorful image. Another example where we've been using deep neural nets to empower our mobile microscopy and sensing tools is this example, which is a label-free bioaerosol sensor. Basically, it's also empowered by on-chip microscopy. At the heart of this device, you have a chip-scale microscope powered by CMOS imagers, where there's a impactor on top of the CMOS. And this is the inlet where we take approximately 13 liters of air per minute and deposit the contents of the air onto a transparent substrate. By comparing before and after, you can actually reconstruct images of the new coming particles and start sensing. Here, deep neural nets are helping us for both image reconstruction and for recognition of what has been reconstructed based on shape and color of those particles. And this enabled us to do label-free detection sensing of mold spores like black mold and different types of pollen particles with more than 90% accuracy in terms of class differentiation, one pollen type versus another pollen type, etc. So in general, deep learning has really been helping us to transform microscopy, whether it's coherent holographic microscopy or smartphone-based microscopy, where you can take a neural net and train that against ground truth benchtop diffraction limited microscope, so that your smartphone's color aberrations or lower resolution due to limited optics can be enhanced, and you can do super resolution and color corrections for these kinds of smartphone-based microscopes to be rapidly performed using neural networks. In addition to this, you can actually establish cross-modality transformations. This is actually going to be very interesting because it opens up the doors for some new capabilities, as I'll highlight in the next couple of minutes. So what I mean by cross-modality image transformation is the capability to establish the statistical transform between one mode of microscopy and another mode of microscopy. By taking a bunch of samples, training samples, and imaging these training samples both with one type of microscope, like a confocal microscope, and another type of microscope, let's say a super resolution microscope like a STED microscope, which is a nonlinear microscopy modality, stimulated emission depletion microscopy, that can beat the diffraction limit of light. And by carefully registering those two sets of images, you can actually ask a neural net to give you an approximate function that can take a confocal and transform it into another mode of microscopy with the features of that microscopy, which means you can perform, in this case, super resolution through transformation. So these are some examples of, once you train this kind of a transformation, how you can take confocal diffraction limited images of, in this case, nuclei of HeLa cells. And this is the same sample image with STED microscopy revealing features that are beyond the diffraction limit. And this is how you actually match the same from just confocal input by performing these cross-modality transformations. And this is another reflection of the resolution enhancement, where we show here 20 nanometer particles that are clustered in different parts of the field of view. Because of the limited resolution of confocal microscopy, they cannot be resolved. These are closely spaced 20 nanometer particles. At the STED output, they're nicely super resolved. And with the neural nets inference, you can nicely resolve them, coming close to STED microscopy in terms of resolving those closely spaced nanoparticles from each other, which means you're actually taking the point spread function of confocal microscopy and shifting it to the left, nicely matching the distribution of these full width half maximum of these nanoparticles that you expect from a STED microscope. These are blind testing results showing you indeed that you're pushing the resolution and the full width half maximum of the point spread function across your field of view to match the distribution of STED microscopy through the network's inference. And perhaps one of the most successful applications of this cross-modality transformation has been to mimic structural illumination microscopy. So SIM, also known as structural illumination microscopy, utilizes structured illumination to improve the resolution of a microscope by having higher frequencies, higher spatial frequencies to be downshifted to the passband of your system so that you can actually digitally synthesize a larger numerical aperture. It uses multiple illumination patterns, but that's what you pay for. These are beautiful reconstructions coming from SIM. At just the network's input, in this case, we're using total internal reflection fluorescence microscopy TURF. But without SIM, you cannot reveal these features. These are clathrin-coated endocytic structures within a live cell. They're they're forming, dissolving, and this is the internal metabolism of the cell that you're trying to reveal here. But because of the resolution loss, you cannot actually super resolve them. That's why you need the SIM microscope. The interesting thing here is that the transformation here nicely approximated the function of a structural division microscope, and at the network's output, you have a beautiful reconstruction that matches the resolution of SIM without the need for the structured illumination. From a single image, you can actually capture with a turf microscope, mimic the resolution of a SIM microscope with much less number of frames and with less photon dose and with less phototoxicity. This is a live movie. This is a movie of a live cell. These are sub-regions of interest, super resolved at the network's output, nicely matching the ground truth coming from structural division microscopy reconstructions. Everything that I'm showing when it comes to an inference is a new sample, meaning that these are generalization results. None of these samples have been used during the training phase before. To further test the generalization performance of this system, here I'm sharing with you a test where we took the same cross-modality transformation network that mimics SIM reconstructions, but this time we've changed the type of object to an embryo, a tissue sample. A live Drosophila embryo is the object here. And the network was only trained with monolayers of cells. For example, if you look at these previous images, you would see that it has a beautiful dark field background because of turf selected excitation. But now we're switching to a different type of a sample where there's substantial background noise accumulating because of the embryo, live embryo, and because of the tissue. So from cells, now we're shifting to tissue without changing the network. Here, it's pure generalization in the sense that the samples are new and it's a new type of a sample. And the idea still works beautifully well, despite the significant increase in the background noise and the statistics of the noise features. Nicely matching SIM results with a single turf image from the field of view. This is a live sample that we're showing here at the turf input. These are network's output. This is the SIM result coming from 9 different structured exposures. These are showing you how you can actually establish these cross-modality transformations coming from data acquired by 2 different kinds of microscopes and perform super resolution, perform certain tasks that are mimicking the new type of microscope that you would like your inputs to look like. One could argue that for some of these, you could take other approaches and utilize existing inverse solutions to approximate the function of the ground truth or whatever microscopy modality that you want to approximate. So perhaps there could be other ways of doing these. But the power of cross-modality transformations is actually beyond just establishment of a forward model. There are certain examples, there are certain problems where you cannot relate input-output relationships between the input and the output. You cannot relate them with a forward model. And that's where data-driven solutions would be key and would enable us to solve for some very difficult to solve problems. And I'll give you an example here where this cross-modality transformation will attempt at solving a very difficult problem where the inputs that I'd like to take will be fluorescence microscopy images of samples, and I would like them to be transformed into bright field microscopy. So the cross-modality here is going to be between fluorescence and bright field. This one is very difficult to establish a forward model because our current understanding of light-matter interaction does not help us easily establish a fluorescence process to be linked to bright field images of the same sample. This is a very difficult forward model to establish, at least with our current understanding of applied physics and light-matter interaction. But that's not the only part of this transformation. This is going to be, in addition to different modes of microscopy, it's going to be changing the sample from label-free at the input to be labeled at the output, which means I'm now looking at a transformation that's going to go from fluorescence to bright field, but at the same time, sample is going to be going through a transformation, label-free to label. So it's a very difficult problem to attempt with standard forward model establishment and inversion of those models. You may be asking at this point, so what? Like, why should I attempt at solving such a difficult, peculiar problem? Well, if we can do this kind of a transformation, we can change the way that we do histology, histopathology. So every time we take a biopsy sample, it goes through this laborious and costly, slow process of staining. Because if you take this biopsy sample and cut it thin, a few microns thick, and look with a microscope, you won't see any contrast. It will be looking like a transparent piece of glass. That's the reason why for the last 150 years, we're staining these tissue samples with chromophores or sometimes fluorophores so that they look under a bright field microscope like this. This is what goes to a pathologist for diagnosis of various kinds of diseases. All kinds of cancer are diagnosed with these types of images after staining. So the question here is, what if I could stop the process here, take these unstained, label-free images, and take their fluorescence image without any external fluorophores? So it's label-free fluorescence. So I'm looking at the autofluorescence of endogenous fluorophores, as superfluorophores that are embedded within native tissue. These grayscale images are still diffraction limited. They have beautiful contrast to it, and they have molecular fingerprint of the autofluorescence processes embedded within tissue. Now, the task of a deep neural net here is going to be taking the same tissue samples after they have gone through this histochemical staining process and train this neural net to establish this data transformation by feeding it with pairs of autofluorescence images at the input and ground truth coming from histochemical labeling, so that the network is penalized till it learns this transformation from texture of autofluorescence to texture of bright field stained images. The architecture behind this learning is called Generative Inversion Network, which means there are two different convolutional neural nets that are fighting with each other. The first one, the first convolutional neural net, which is a unit-based structure, it's trying to learn this transformation between autofluorescence images and histochemical stained images so that it can generate an image that mimics, approximates the histochemical staining process happening, and then bright field imaging, subsequently digitizing the image. This is the artist. This is basically the virtual painter or virtual histotechnologist. The discriminator is another convolutional neural net that's penalizing the generator every time it can differentiate what is histochemically stained and what is virtually stained. So the discriminator is the critique, and its job is to improve the performance of the generator. This is not one of those noise input, artistic output type of GAN structures. This is a structurally beautiful microscopic image that has everything of the tissue sample at the subcellular, submicron resolution level. That means when we're training this generator, we're not just looking at discriminator loss, we're also looking at structural loss terms. Mean square error and total variation are used for the generator to be faithful to the nanostructure of the tissue that it's imaged. And this is very important. This is as beautiful of a microscopic image as standard histology coming from bright field microscopy. They have the same numerical aperture. The generator task is to virtually stain it while being faithful to microstructure. At the end of this competition between the generator and discriminator, nobody wins. There's an equilibrium, which means the generator deceives the discriminator 50% of the time. Flipping a coin is the solution. That means you have a beautiful generator that can now virtually stain tissue. In the next few slides, I'll share with you what we've done with those generators post-training, show you examples of human tissue sections that are new patients testing the generator against humans staining tissue. We've done this with many different organs and stain combinations. What I'm sharing with you here is salivary gland tissue. It's H&E stained. What goes into the neural net are these autofluorescence images, standard DAPI filter. Basically, you shine blue light and look at, with a passband coming from a standard off-the-shelf DAPI filter, you look at autofluorescence processes. It's contrast enhanced for your eye. This is just for your eye to see that there is a beautiful microtexture in there. that is at the heart of the success of the neural net. Anyways, these go into the neural net, rapidly reconstructing a beautiful virtually stained image, nicely matching what comes out of the histology lab stained by humans, perhaps in 2 hours. A good H&E stain takes approximately 2 hours by a human. So you can do this in less than a minute with a GPU. In addition to H&E, which is one of the most commonly used stain types, in addition to H&E, you also can apply this to other types of stains, spatial stains, they call it in histopathology. This one is a Jones-Silver stain, and this is kidney tissue sections. Again, DAPI images are at the input. Jones-Silver stain output images are shown here. This is what comes out of histology lab stained by humans after approximately 3 hours. A good Jones-Silver takes around 3 hours, and it's a laborious process that involves inspection of the chemical staining process under a microscope by a human. That's why Jones-Silver stain is significantly more expensive per slide than H&E, at least a factor of 10. The insurance cost for Jones-Silver stain is at least a factor of 10 more expensive per slide than H&E. Some other examples are shown here. Liver, lung tissue sections. DAPI images are shown here as the network's input. This is another type of stain, Mason's trichome. Also, it's a laborious and expensive stain to perform, around also 3 hours. And these are beautiful virtual stain images, nicely matching what comes out of histology lab, perhaps in one afternoon, showing you that you can actually perform H&E and other types of spatial stains. These were stains that are not molecularly specific. They're chromophores that are binding to different parts of the tissue to give contrast. But there are also immunohistochemical stains that are more difficult to apply. This one is a HER2 stain, IHC, immunohistochemical staining of HER2, which is basically a key biomarker. It's a surface receptor and which shows an increased expression level for certain groups of breast cancer patients. That's why staging of HER2 would be very important for targeted therapy. And that's why this is a frequently applied staining method. It takes about a day. Immunohistochemical staining is slow because it's molecularly specific targeting surface receptors of the cell membrane. And we have shown that you can actually capture multiple autofluorescence channels, FITC, DAPI, Texas Red, Cy5. And through this rich information of autofluorescence, we were able to create a UNet-based with skip connections deep neural net to do beautiful virtual staining, bypassing the need for immunohistochemical staining, providing basically a shortcut and a high fidelity reconstruction for these virtually stained HER2 IHC immunohistochemical stains. These are not just two images that we can compare and look as engineers, as scientists, to say that they are really good. The virtual stains, they look as good as the standard histochemical stains. Well, that's good to start, but you have to also ask the opinion of diagnosticians, and that's what we've done. Basically, what you see here are some blinded studies, and there are many of these tables in our supplementary information for different papers. Basically, we've given board-certified pathologists these images, half of which were virtually stained and the other half were histochemically stained. They did not know which one is which. They were just scoring these. And here we asked them to score the quality of the stains in terms of nuclear details, cytoplasmic detail, extracellular fibrosis, and they were giving scores. Based on these kinds of tables, we come to the conclusion that there is statistically no significant difference between the stain quality achieved with our images versus standard human-based histochemical staining. In fact, if you look at the scores, we're slightly better, but the p-score is not significant, which means we're on par with standard of care coming from histology labs. On top of the stain quality, we also gave these images corresponding to different cases to pathologists for them to diagnose conditions of the patients. And the same conclusion, the diagnostic accuracy or the diagnosis of these pathologists were on par in terms of what they can achieve with our images, virtual stain versus histochemically stain. So we are preserving the quality of the stain and the diagnostic features of interest for diagnosticians to basically look at the patient specimens and make a diagnostic decision. So what are the major advantages of virtual staining technology? So why should we be so excited about this kind of a framework? First of all, virtual staining standardizes the staining quality. When you look at humanist technologists, this is H&E stain slides from UCLA Health, you can see there's quite a bit of variation. From histotechnologist to histotechnologist, from run to run, you see variations in the staining quality. This is not good for human diagnosticians. This is also not good for AI-based methods to look at, for example, tumor margin detection, classification, or staging of tumors, etc. Those kinds of machine learning methods as downstream molecular analysis, they would require more consistent images, and variations of the staining quality is a hurdle for human pathologists and AI-based analysis of pathology slides. The consistency of deep neural nets is a blessing here, because it's taking molecular fingerprints of autofluorescence at one or more channels and creating beautiful and standardized images, which is great for standardizing diagnostic decisions downstream. But one of the, I think, most exciting aspects of virtual staining is that you can create multiple stains from a single cross-section. Today, if you want to look at a panel of stains, for certain conditions, the diagnostician would not just ask H&E. They will ask H&E and some other stains, because they all reveal different features. Well, that means you will have to cut tissue more and deplete tissue and damage tissue, and these are going to come from different parts of the 3D tissue block. But the good thing about virtual staining is that from a single autofluorescence cross-section, you can actually stain all four, in this case, of stains that would be needed for the case at the same time, nanoscopically registered and without depleting tissue. The tissue is preserved, and you don't need to call the patient back for another biopsy. Believe it or not, a lot of the biopsies that we give are redundant because the analysis that they perform deplete tissue, and you need more tissue to do more analysis. Virtual staining will preserve tissue and eliminate unnecessary biopsies to be performed. You may be asking, what other methods of imaging, what other contrast mechanisms can you use for virtual staining? Is autofluorescence the only way to do virtual staining, eliminating toxic chemicals and staining procedures? The answer is, you can actually utilize other label-free imaging methods. For example, holography can be also used. So quantitative phase imaging, we've shown a couple of years that quantitative phase images coming from a holographic coherent microscope can be utilized as input through refractive index, complex valued refractive index information to also do virtual staining. So the other forms of label-free contrast can also be utilized in general for virtual staining. Although we believe autofluorescence is one of the most powerful molecularly specific way of looking at endogenous fluorophores within label-free tissue, there are other ways of extracting information from tissue that can be used for virtual staining. In one of our very recent work, actually, we used reflectance confocal microscopy in a label-free manner to also generate sufficient contrast to do virtual staining. This is different than previous results that I've shown you in the sense that here, we're not taking a biopsy out. This is biopsy-free because reflectance confocal microscopy has been FDA cleared for use in dermatology practice. The good thing about it, that is, without cutting tissue, by just actually with a probe coming in contact with the skin, you can go deeper and capture sections of tissue with a reflectance confocal microscope that has this grayscale image. It looks like autofluorescence images that I've shown you, but here we're looking at reflected light intensity at different cross sections coming from a biopsy-free, label-free method. And using a similar strategy, we were able to actually transform these images into H&E-like images all the way down to dermal epidermal junction and superficial dermis layers to create virtual histology without taking a biopsy through the contrast mechanism of reflectance confocal microscopy. So these were highlighting how you can use label-free contrast all the way from autofluorescence to quantitative phase imaging and perhaps even reflectance confocal microscopy as the information channel to do virtual staining. But the beautiful thing about this approach is that you can actually form a network of transformations from a label-free sample to one stain, another stain, and another stain. Now, if you have this network, you can also ask yourself a question. Can I do stain-to-stain transformation? What if I'm too late? What if the sample was already stained with H&E? Can I give you H&E bright field images that we have in our databases, and you can transform them into different types of stains without access to tissue? So this network enabled by virtual staining methods led us to do stain-to-stain transformations. And this is especially powerful because H&E stained images are all around us. We have millions of these images stored in our databases as part of different hospitals. They have been already stained. What if we could actually take those and restain them virtually into different kinds of channels where diagnosticians can actually start to get more out of these images that are already stained with H&E through stain-to-stain transformations enabled by virtual staining. So we've done a demonstration of that to show the utility of this capability for a clinical workflow. And here, we applied it to kidney needle core kidney biopsies. These are transplant rejection cases where patients were having issues. They were transplant patients. And when they come with some symptoms, the clinical workflow would require to start with an H&E of the needle core biopsy, and the diagnostician here would write a report, and most likely this would not be sufficient and would request 3 additional stains. This is the workflow. Of course, if this is sufficient, you will stop the workflow there, but most often diagnosticians would like to see spatial stains, and this takes a while. To get Jones, Mason's trichome, and PAS stains takes a while. During this entire period, back and forth between the diagnostician and the lab for additional stains, it may be a couple of days, depending on where you are in the world, maybe a week, during which the patient is suffering and perhaps hospitalized, and you don't know what to do. So what if you could actually quickly run an H&E and give the diagnostician the H&E along with basically these spatial stains? That was the hypothesis here that we've tested, to show that stain-to-stain transformations can help us to reveal more information about the patient without the need for actual histochemical staining of these spatial stains. So that's why we took a bunch of cases, some of which were organ transplant rejection cases, and gave our diagnosticians H&E only images, asked them to diagnose the case. And then after some washout period for them to forget those cases, we gave them the same thing, but this time histochemically stained H&E, the same, plus virtually stained spatial Jones, Mason's trichome, and PAS virtually created images, so they can actually get the full picture. The hypothesis here is, can that improve their diagnostic decisions? And you know, the short story, the message of the story is that indeed we have seen with the virtually transformed stain-to-stain transformations, we have seen improvements on the order of 46% of the cases that they diagnosed. They improved their diagnostic accuracy and improved the decision with respect to H&E only. There were only 3 discordances, and we found out that actually one of them was a diagnostician error by looking at other diagnostic reports coming from the same comparison. So indeed, the value is making some of those diagnostic decisions better and faster without the need to go back and forth between histology lab and the pathologist, the diagnostician. To sum up, virtual staining is enabled by cross-modality image transformations from label-free images or labeled bright field images to different types of stains. It's a network of stain-to-stain transformations. It saves expert labor and time. It also eliminates a lot of reagents, personnel time, monitoring under a microscope, and saves in general cost. One thing that I haven't mentioned is it also is a green technology in the sense that through staining of histochemical staining of tissue, we're wasting millions of liters of water every year because of the toxic chemicals and the washing period involved in this chemical process. Literally millions of liters of water is wasted. So that's also going to be eliminated to make the process faster and greener in terms of how you stain tissue. Another major advantage is tissue preservation. You can do multiple stains from a single cross-section and you do not deplete or destroy tissue. And finally, it standardizes stain quality. So which means for pathologists or for downstream machine learning, consistency of the virtually stained images would be the key for perhaps downstream success. This technology is also being commercialized by a startup that we founded in 2019. And so far, it's moving forward very fast and very exciting. We also expanded this technology to animal tissue, and we can also do various different toxicology reporting and images of different organs of animal models using virtual staining technology. That becomes even more valuable to speed up the process of, for example, an FDA approval of a drug, or it's also extremely advantageous because a lot of these organs of a mouse, for example, are tiny, so that the tissue is very valuable to preserve. All of this, of course, needs more validation. These are some proof of concept experiments tested with a lot of inputs from pathologists, diagnosticians from UCLA, USC, Kaiser Permanente, UC Davis, UCSF. So a lot of input from our colleagues from pathology departments across the US has been helping us to push this technology, validate it, improve, and get closer to actually utilization in research, pharma, and hopefully in clinical settings. So to summarize and conclude, I think computational imaging and sensing is going through a transformation with the help of especially data-driven transformations we're seeing enabled by deep learning methods. And what I'm especially excited about this transformation that we're seeing right now is image reconstruction tools, image enhancement tools, image transformation tools are getting beyond just our understanding of light-matter interaction, and we can attempt at solving problems that we do not have a forward model. We do not know how to relate autofluorescence with bright field, for example, but that's not a game stopper right now, and we can go beyond that to create some unique transformations that help us with our clinical needs. So that's where we are, and I think beyond these, what I've shown, there are many other applications being pursued by the community of scientists and engineers in optics fields globally. With this, I'd like to conclude and thank you again for having me here today. I'd like to also acknowledge all of our funding agencies, students, and postdocs behind this work. Thank you very much.
Okay, thank you very much for the very inspiring talk. So we've seen many really fabulous results slide after slide. So I think there should be a lot of questions. So if you have time, please. I'll just look at the attendees, please write down your questions on the Q&A, and I can read out the questions. So when you examine the accuracy of the neural network output, how do you consider the reference image? So in other words, where the ground truth comes from. So
great. So when we evaluate the success of these different methods, the ground truth is coming from another microscopy modality. For example, let's talk about confocal to state transformation in this example. So the same samples were imaged by a confocal microscope, which was housed in the same STED microscope. Basically, the same platform enabled us to switch from one mode of imaging to another. Therefore, for our training images, we were able to acquire confocal images of those and then STED images, and then register them at the nanoscale to create a training image. Once that training is done, such as this case where it's the testing example right now, you do the same thing where the ground truth imaging method captures what the ground truth looks like, and you compare the network's output with respect to this ground truth. Here, we look at various different matrix. We look at mean square error. We look at the difference between images with a color map where you take literally pixel by pixel differences and try to understand the level of difference between the two images and quantify potential artifacts, etc. Sometimes, for example, here we are looking into point spread function, like we are looking at gratings, we're looking at individual particles to also quantify resolution. So I haven't shown, but many of our papers report these kinds of PSF analysis, but at the same time, we sometimes also put structured objects where we know the periods. So which means if I have a resolution test target, I can just put it in front of my input type of microscope, and then I look at the network's output image, and then I know the ground truth because that's a resolution test target that I fabricated. So there are these kinds of tests as well. It depends on what network you're targeting and how you're testing it. If you're testing it with features that you wrote with nanofabrication methods like e-beam lithography, then you know the ground truth from e-beam lithography. Sometimes we use slit microscopy as a ground truth. For histology, that's a different game because for histology, I can't fabricate things like in a clean room. For histology, the ground truth is human histotechnologists. So which means the workflow is like this. I collect biopsy samples from a bunch of patients, whole slides. These are thin sections, label-free, put on glass slides. 20 patients, 100 patients, depending on the data set that you want to have. These label-free samples look like this. We image them, we digitize them, and capture these billions and billions of pixels of how they look under different autofluorescence channels. Then we send them to a histopathology lab at UCLA or nearby labs, and they send us bright field images of the same cases. Sometimes they make mistakes, they distort tissue, sometimes they really tear tissue because the tissue staining process is not very repeatable. Sometimes there are issues with tissue flipping, cutting, and stretching. We examine those and we remove all the garbage that is not high quality staining and that has artifacts. The rest, we divide into small sections and register them with our texture coming from autofluorescence channels. This is an iterative registration process where every small patch is registered, cross-registered to images coming from histology lab and mapping patch by patch the inputs that we've captured in autofluorescence channel as shown here. So this is the training process. During this process, we take some of the patient samples and leave them as blind testing results. And those are the ones that we look at structural errors between, for example, virtually stained images and histochemical stained images. We look at their color distances. We look at their structural cross sections to show that indeed, in terms of the structural loss term, the mean square error and total variation, we're minimizing the distance between the two images. And on top of that, this is the engineering matrix that we compare. On top of that, we give these images, blankly created images, to board certified pathologists for them to tell us basically scores about these images. This is a different matrix. This is basically from the perspective of a diagnostician. And that's essentially probably more valuable than just looking at distribution of nuclei, size of nuclei, cross sections in intensity, color distances between the ground truth coming from histology versus your own virtually stained images. So that's why, depending on the application, you need to set different validation, different testing strategies to show the efficacy of your output. And for virtual histology, honestly, diagnosticians' decisions and scoring has been the most important one, especially from the perspective of utilizing them in the workflow.
Thank you very much for the kind answer. So the next question is so we really have a broad audience today. So what kind of background is needed for students to work in this area of biomedical imaging? Are solid programming skills needed? Or is it possible to start with just basics of Python, for instance? So I have a related question, I think. So your work is based on optical imaging, but did you find that insights in imaging was more important, or like building new architectural structures for deep learning more important in your works?
So, great. I think, so let's, two questions, the architecture and learning. I think obviously a lot of what I've shown is TensorFlow based and PyTorch, some of it, depending on the student. Some students like to work with PyTorch. So yes, Python is something that is going to be great for the students to learn, and at least with one of these commonly available deep learning platforms, you should start basically playing with different models that are available in GitHub and other parts, other dissemination methods where people put their network models with some data. You can also find some of our own network models in GitHub and some data for you to test. So I think that's a good start to learn some TensorFlow, or if you don't like TensorFlow, maybe PyTorch. I think those are two that my students like to use. In terms of network architecture, so for different applications, there are, I think, different network architectures that are providing very valuable, I think, frameworks. We have been heavily using a UNet structure with skip connections and time with different kinds of attention gates. So all the modern tools that help efficient learning and better inference are upgrading the architecture, and we have been using those. What we like about UNet for microscopy applications is its structure that downsamples and upsamples, so that you can actually have a very distant performance for relatively bigger features and relatively smaller features at the same time, because you're learning at different spatial scales through the downsampling and the upsampling path. So is this critical? Is this absolutely the must network architecture to use? I don't think so. I think when you talk about a neural net, there's no unique solution, because neural nets never provide a unique solution. They always provide good engineering approximations, because deep learning is all about approximation. Within a certain error bound, every time you use the same data set with different randomization and with different batch size or batch sequence, you will get a different network, slightly different parameters, filters, etc. And that means it will perform the same, almost unnoticeable to you, but with slightly different errors and with slightly different coefficients. That means the solution space for a universal approximator like a deep neural net is so deep and rich that you can actually repeat some of what we've done with a different network architecture. And I think the question nowadays that the field is fairly rigorously working on among many directions is how to make learning more efficient, where you have less access to ground truth, or perhaps no access to ground truth. And I think we're seeing that more than the network architecture, the way that you pose the learning problem with constraints coming from the physics of the problem, like physics guiding the learning as setting some rules that we know must be satisfied because of physical laws. Those are helping restrict the learning to a certain direction that is not as data hungry. And I think those are interesting directions that my lab and many others in the field are approaching to cut down the data size, speed up learning, make learning also parallel to physical understanding of your problem, so that could replace the need for more and more and more data used during the training process. So yeah.
Yeah, so thank you so much. So I'm not sure if you have some time. I know it's very late right now in California. Maybe one or two questions, is that okay?
Please, yes.
Okay, so I'll just read out. So it's about the STED experiment. So how does the results compare to commonly used like advanced versions of deconvolution?
Great question. We have these results in our paper. Let me see if I have those slides. I don't have those slides. Let me stop. Basically, if you look at the Nature Methods 2019 paper in the supplementary, there are those comparisons to Lucy Richardson, deconvolution, and others. Please give me 1 minute. I'll open up another slide deck to show you that one.
And while we're open, there was another question. How many input images did you need? I think it's also in the paper, but
yes, absolutely. Let me see. This is the PowerPoint. Yes, this is the right one. Well, perhaps I should just open the paper. Give me 1 second. So while I'm searching that figure for, it's here. Okay, I don't have to search. So let me share my slides. So do you see the slide?
it's loading. Yes, we see the slides.
Okay, so actually this is, I think there are more of these images, but you can compare basically, this is one form of super resolution where it's like 0.4 numerical aperture to 0.75 numerical aperture, extending the depth of field and resolution by using network inputs. So the network's inputs are shown here. These are different parts of a stained cell. This is the DAPI channel, this is the FITSA channel, and this is the Texas red. Network's input are shown here, lower resolution for a reason, because we're doing super resolution. This is the network's output trained for DAPI, FITSA, and Texas red separately. These are two different deconvolution methods, non-negative least square and Lucy Richardson, and they're shown here. You can clearly see the cross sections and the improvements. This one, the DAPI channel, is highlighting a beautiful reconstruction. In fact, you would be surprised that this is actually beating the ground truth. And for example, you may be wondering, why is this better than the ground truth slightly? I mean, I hope you can clearly see as clear as I see it with my slide that network is slightly beating the ground truth. There's a reason for that. The reason is the network has generalized to look at an extended depth of field image coming from the low NA of the input. So whenever it does super resolution, it does that over a larger depth of field, which means the ground truth has beautiful numerical aperture, but limited depth of field. As a result, some of the 3D objects that are out of that plane will be looking defocused here due to the 3D nature. But the network beats it because of, again, due to the 3D nature. And this is highlighted here in another blind testing, where we're looking at a mouse blood vessel, where the network input has a large depth of field, but low resolution because of the limited depth of field. The network has been trained, and this is now a blind testing result. Look at, for example, these arrows where you clearly see a 3D structure that is being brought into focus despite the blood vessel being 3D. And if you look at a ground truth image of the same, some parts are beautifully in focus as expected from the 0.75 NA. But look at this region, it's out of focus. That's because of the 3D nature. How do we know that? If I take the same sample and do an extended depth of field image synthetically by Z stacking and capturing multiple images with the same numerical aperture with 0.3 micron spacing, you can synthesize a new ground truth, which has high NA, but at the same time, larger depth of field, extended depth of field. Only then you see the network's output nicely matching. That's actually a very interesting feature, which is kind of counterintuitive, but you can beat your ground truth with deep learning. It's all about generalizing and keeping the advantages of your input at the output. And this is a perfect example of that. And it's also highlighted here. Network's output, single height. This is ground truth, beautiful resolution, poor somewhere. This is the extended depth of field, and these are the difference images between ground truth networks, output, single ground truth versus extended depth of field. So as you can see, we match to the extended depth of field. And this is another validation of the same thing, which means the ground truth, because objects are at different points, has a very large full-width maximum distribution with the point spread function coming from these 20 nanometer particles. At the network's output, we zip them. And that's the extended depth of field coming from network's output. So that's essentially the comparison to different convolution methods and how you can actually extend the depth of field with respect to the ground truth. Coming back to your question about how much data you need for something like this, it depends on the transformation. For these kinds of transformations, a good number, empirical number that we know of is at least 10,000 image pairs. Each image pair is a few hundred pixels by a few hundred pixels, let's say 200, 300. So you have ground truth input image pairs that are coming from unique objects. 10,000 is a good number to have to start one of these models. For more difficult models like HER2 virtual staining or STED super resolution or SIM structural elimination microscopy super resolution, that number we have increased up to 50,000, 100,000 plus sometimes. Is this a problem? Not really, because microscopy tools are extremely fast. The high throughput nature of microscopy makes it actually very exciting for capturing over a weekend. If you have really a good high throughput scanning microscope, over a weekend you can actually collect sufficient data, because some of those microscopes really scan like a terabyte data of microscopic images within an afternoon.
Okay. So thank you so much. So we're actually over the time. So in the interest of time, I think we should close the webinar here today. And so thank you once again for the very inspiring talk and also the very kind and detailed explanations. Okay, so
thanks for having me. It was a pleasure.
So, yeah, we hope to invite you here in person soon. Maybe, yeah, hope the pandemic gets settled soon. Yeah.
Look forward to it, and likewise, if you, your students, and your colleagues are in California for a meeting or a conference, would love to have you come by UCLA, and would love to meet with you and your colleagues.
So thank you so much. Okay.
Thank you.
I hope you have a great evening. Thank you again.
Thank you. Have a good afternoon there, and look forward to talking with you in the next opportunity.
Okay. See you.
Bye.
Thank you.
Take care.
Bye.